Tuesday, everyone. Thank you, Matt, very much for inviting me here. It's a privilege to speak in front of such an audience today. Before we start, I thought I would just ask a few questions. Who here knows that you can go to university and study a subject called data visualization? Raise your hand if you know that that's possible. Okay, that's pretty good, actually. And who here knows that there's a community called visualization or data visualization that meets at conferences and stuff like that? Okay, and you're cheating a little bit, but okay, that's good. That's a good start. So I should probably get the slides going. So to sort of honor this special occasion, I thought it would be kind of fun to give an uncertain talk. So I don't know, what that means is I don't know how this talk is going to end. Right? That's pretty full of suspense. So what we're going to do is, I'm going to just give a brief introduction to the topic of data visualization and uncertainty visualization. And then at some point the talk stops and we can go in 8 different directions or 8 different demos of different kinds of visualization of simulation data. So I'm going to ask the audience which direction they'd like to go in. Right? We won't be able to look at all 8 demos. You can only pick 1 or 2. So I thought I would ask the audience, with a show of hands, which one they might like to see first, for example. Is that something this audience might be able to help with?
Sure, we can.
Good, good. So a little background, a little bit of fun slides. So we could say that we're living in the age of digital uncertainty, and I think this is something that everybody in this room is very familiar with, but you may never have seen a diagram of it. Right? It's a diagram that describes a ubiquitous pattern of knowledge evolution that we're all collectively experiencing right now. Right? It starts with a real-world challenge. Right? Ben is trying to make the world's fastest car. That's a challenge, right? So there's a physical approach to that challenge. Like ultimately, we want to actually build something real in the real world. But it's not very easy. We run into problems, right? If we try to build real-world bloodhounds, for example, it's very expensive. We can't just make a million prototypes. So when we run into problems in the real world, like feasibility problems, cost problems, optimization challenges, we depart the real world and we jump into the digital world, right? The world of simulation and CFD, right? For solutions to our problems, right? That's what this dashed line is, jumping from the real world to the digital world. And then we work on digital solutions like building software that does some computation, right? Or using an app to get something done. Right? We build digital solutions to our real-world problems, but then we run into another challenge, another digital challenge, and that's the data chaos and the data uncertainty challenge. Right? We have a lot of data uncertainty already at the conceptual level. Right? For example, who created the data? Where is the data? How much data do we have? Who has access to the data? That's some conceptual uncertainty to our data chaos. And the premise of this talk is the key to resolving the data chaos or the data uncertainty is data visualization, right? Data visualization is the next step in our learning process and our knowledge evolution that's going to save the world from the uncertainty that we bombarded with the data. So visualization or interactive visualization is good for exploration. This is the case when you don't know what your data set is necessarily. you're not an expert, you aren't the person that created it in the first place, and you want to just find out what it is, if there are any patterns, any outliers, any trends. Data visualization is good for analysis. That is when you are already an expert, right? Maybe you collected the data yourself, you generated it yourself, and you want to confirm or refute a hypothesis. This is what I think most people associate with visualization as presentation. After you've done exploration and analysis and you want to communicate the results to an audience, like this one, data visualization is very good for that. It's also good for acceleration. So that means we can make decisions much, much faster, and we can make observations much quicker using data visualization than in the case compared to reading the numbers one by one manually. And another nice thing about visualization is it increases confidence. Or the inverse of that is it decreases uncertainty. Right? Visualization gives us more confidence that what we're doing is either incorrect or incorrect. The more we can see the data, if we can't see it, it's not very useful. Right? So by visualizing data, we increase our own confidence. This is one of the major strengths of visualization, because usually what happens is as soon as we start to visualize data, we see errors. We see problems that jump out immediately. Okay, here's a little view of uncertainty from the world of visualization in computer science. It might be slightly different from your version, so to speak. But this is how a lot of the people in data visualization see the world of uncertainty. It's what we call an uncertainty pipeline, which is kind of a paradox, actually. There are different phases of uncertainty. So we have uncertainty in what we call the data acquisition or generation process, right? That's the measurement, the simulation, the modeling. That's what everybody here does. You know that that data is associated with uncertainty. Measuring devices have uncertainty, right? And computation is associated with uncertainty. But the uncertainty propagates down the pipeline. So as soon as we do some enhancement on the data, we add uncertainty. So things like interpolation or filtering or resampling adds further. That's what we call data enhancement. Adds uncertainty into the equation. What this talk focuses on is this part of the uncertainty pipeline. As soon as we take the raw data and start mapping what we call geometric primitives onto the data, there's also uncertainty involved. But when we start to visualize the data, we map it to color or different kinds of shapes, curves, opacities. There's also some uncertainty associated with the computer graphics side, right? That's when we calculate things like visibility, shading, and animation. We don't usually convey that uncertainty. It's usually implicitly hidden, but there is uncertainty in the computer graphics part of the pipeline. And then someone asked earlier today about this. There's uncertainty in the interaction phase of the pipeline. So when a user is actually looking at the data and they're interacting with it, they might be wondering, okay, which parameter am I supposed to tune right now? What did I just do to the viewpoint? I don't remember what I did to the viewpoint. Like, there are lots of user parameters here. I can't remember which ones to use and which ones I already used and which parameters I set them to, and so on. So there's uncertainty associated with the interaction too. Right? And in this talk, we're going to see some examples. So uncertainty can be represented in data visualization by color, textures, opacities, positions, sizes, thicknesses, shapes, and curvature. We're going to see some examples of that. Here are just a few early examples of uncertainty visualization, right? These are comparing different streamline paths, right? Depending on the integrator you use for your streamlines, you can get different paths, right? Because different integrators have different accuracy. And these are visualizations that compare different integrators and their accuracies. This one's called an uncertainty ribbon. This is comparing the paths using line segments and other kinds of things like twirling hook batons. This is early work on this subject back in the 90s. We just happened to do some work on uncertainty associated with isosurface rendering. So we generated multi-resolution representations of some medical data, high resolution, middle resolution, and low resolution. And each time you change the resolution of the data, you add an error or uncertainty. And we did some experiments to visualize that uncertainty. And it's just using colors and textures. And it's not very impressive work, but it happens to be highly cited and popular on Google because it's one of the earlier experiments. Like if you Google uncertainty visualization, you can find something like this. Okay, so here comes the uncertain part of the talk. So we have 1, 2, 3, 4, 5, 6, 7, 8 different demos we can look at. I'm just going to briefly describe 8 different options, and when I'm describing that, maybe you can think of your favorite 1 or 2, and then after, we're going to ask the audience which one they prefer by a show of hands. Okay? So the first topic is automatic streamline seating. So I think a lot of people in this room have spent time positioning a rake, like with their mouse and things like that, to try to seat streamlines. Well, it is possible to come up with an automatic algorithm to do that, so you don't have to spend all day doing that. It's another, the interactive uncertainty is heavy in that space. We have another one, the visualization of seating sensitivity. So that's where we talk about, again, the uncertainty associated with interaction. So you may have wondered, will a small change in space have a large effect in my output, or the opposite? You can actually visualize the sensitivity of your simulation to see where small changes in position result in large changes in the output. We can construct streak surfaces. That's another example of visualization from simulation data. So I think everybody here knows what a streak line is, right? When you inject dye into your flow and then you trace out the path that it follows. An unsteady flow. Well, we can also construct things called streak surfaces, which are the next higher dimensional equivalent to streak lines, which are 1D curves. We also worked on automatic stream surface placement. So Ben showed us some nice stream surfaces in his talk. So stream surfaces are the next higher dimensional equivalent to streamlines. So streamlines are curves that are tangent to the flow. Well, stream surfaces are surfaces, 2D manifolds that are always tangent to the flow. And we developed algorithms that place them automatically in space. These are sort of more the basic research. These are a little bit more basic research oriented, more focused. These are more applied. They have more specific applications. We studied applying different visualization techniques to flow through a cooling jacket. Right? That's the cooling jacket that you find in your engine, and hopefully it keeps your engine from overheating. Right? I think there are probably some people in this audience that study the automotive engineering and automotive simulation. We also studied flow through a combustion chamber. So in the case of a diesel engine and a petrol engine, visualizing the swirl and the tumble motion inside those combustion chambers. I think that's something we worked on. We developed something called texture-based visualization. So texture-based visualization is an alternative to your classic streamline color mapping, and you cover the whole space with some sort of a texture. and then you smear the texture and the direction of the flow to visualize the behavior. And then we've also worked on the marine renewable energy problem. So this challenge of placing marine turbines in the Bristol Channel, right? How do you optimally place these marine turbines in the Bristol Channel such that you get the maximum amount of energy extraction from the tidal flow? So that's another kind of visualization problem we worked on. Now we can't talk about all 8 of these, so the audience is going to have to choose which direction to take. Right? So raise your hand if you're interested in the first topic, the automatic streamline seeding. Okay, it's not going to be that one. The seeding parameter sensitivity. 1, 2, 3, 4, 5, 6, 7, 7-ish. Streak surface construction. 1, oh no, person, okay. I like this one. Automatic stream surface placement relates a little bit to Ben's talk. Nope. Visualizing flow through the cooling jacket. Anybody interested? 2, 3, 4, 5. Okay, 5. Visualizing swirl and tumble motion. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6. Okay, so that's second so far. So this was first, right? This is second. Texture-based flow visualization. Anybody interested in that one? 1, 2, 3, 4, 5, 6, 7. Ooh, okay, 7. So tied for first.
Oh.
And then the search for wet green energy. Oh, okay. That's a clear first then. Okay, interesting. I had no idea that would be the most popular one. So we'll go over this one first, and then there was a tie between the seeding sensitivity and texture-based visualization. We could have another round of show of hands if we have time, depending on what Matt decides. So let's look at the search for wet green energy. So we worked for a while with the Marine Energy Research Group at Swansea University. Probably there's some people here that know that group and have worked with that group, Ian Masters and so on. And they're studying the problem of marine turbine placement. In other words, where can you place these marine turbines in the Bristol Channel such that they draw the maximum amount of energy from the tidal flow? Right? And they're trying to answer questions, for example, like how far apart do the marine turbines need to be in order to not interact with each other, for example, right? And how far downstream does one turbine need to be from another before it can gain the maximum, or draw the maximum kinetic energy from the flow, right? Because every turbine is going to collect kinetic energy or convert kinetic energy from the flow, and it will affect other turbines and the flow downstream from itself, right? So the goal was to understand the flow around the turbines for optimal placements. Right, the analog solution is to install turbines. That is the disadvantage of marine turbines, the expensive installation and maintenance compared to wind turbines. Right? And so they simulate, perform lots and lots of simulations about how to place the turbines. And we came up with this visualization solution that uses multiple coordinated views of the data. That's what we call it. So we have the classic spatial view, which is what you're all familiar with. Then we have a high parameter space view, also known as the parallel coordinates view. Then we have a velocity histogram view. We have a histogram table view of the data. And they're all coordinated with each other. That means I can make a selection in one of the views, and the other views are updated automatically and synchronized to reflect that selection. So let's look at the demo. So one of the basic questions is that the engineers ask is, where's the reverse flow? So you have downstream flow and you have upstream flow. Upstream flow is bad because we can't convert the upstream flow into kinetic energy the same way we can with downstream energy, downstream flow. So just one of the fundamental questions is, show me, or where is the reverse flow? And this is somebody trying to visualize the reverse flow using TechPlot and failing, right? Because they don't know where it is, right? That's the question, where is the reverse flow? So, but we can ask that question in a trivial sense in the multiple coordinated views. This is a histogram of the reverse flow direction, or the x direction of the flow, and the user can simply select the negative values in the histogram, and then see the corresponding positions in space of the reverse flow, right? So the reverse flow is right behind the pylon, that structure that holds the marine turbine in place. So as the flow passes the pylon, creates vortices, and then comes backwards. And that's lost kinetic energy, right? So it's a simple question we can ask if we design the right visual interface, right? For example, this one. Right? And then what they want to do is make decisions that minimize the reverse flow. How can we construct a geometry that minimizes or eliminates the reverse flow so we can draw the most kinetic energy out of the tides? And this is a distortion view of the spatial domain, because the spatial domain is elongated along x in such a way. We have a user option that shrinks it down so we can get the whole spatial view in a convenient window, right? And that's a zoomed in view of the reverse flow. So you could spend days or years trying to position a seeding rate to find those reverse flow positions, or you could do it in just a few seconds, right? Selecting it in one of the views here. And that's what we call a velocity histogram, which shows a histogram of vectors as opposed to a histogram of scalars, which is what we normally see. Now the blades themselves are not simulated explicitly, they're simulated implicitly using this blade averaging technique that we won't get into. So the blade geometry is not explicitly modeled. We can't see the blades. So the question is, well, where are the blades, right? And we can select the blade positions really trivially using our interface, right, along the parallel coordinates. So we can just select the blade positions, and we can see the blades using glyphs in the space, right, in a trivial way, using this multiple coordinated views approach. Right? So those are the blades. And those are glyphs that are actually visualizing the flow at the blades. Right? We're zooming in on the glyphs, so they're pointing in the downstream direction. Right? And this is a histogram of those velocity vectors, the velocity histogram, all around, centered around the blades. Right? And those are streamlines seated at the blade positions to find out what happens to the flow after it hits the blades and carries on downstream. That's what we want to visualize. Only the flow that hits the turbines and moves on. And we want to know the extent to which the energy propagates and the space that it affects, right, after it hits the blades. Right? And this is a good way to visualize that interaction. So that's the user making some selections inside the parallel coordinates view. Parallel coordinates, for anybody that doesn't know, is a way to visualize the high dimensional space. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dimensions in this simulation space that we could focus on and visualize. And this is a way to visualize it in different dimensions. So we can also use this method to visualize the flow with the most swirl. So what are the properties that the engineers were interested in or are interested in? Showing the flow with the most swirl, the most helicity, right? And that's a trivial process in this visualization. We can just select the portion of the flow with the highest turbulent velocity, right? We can just make a selection here. And then streamlines are seated at the positions in the domain with the highest turbulent velocity, right? It's basically what it is. It's a knowledge-guided seeding process. That's what we're seeing right now. And we have this vast parameter space, and then we use the domain expert knowledge to position the seeds, right, in an automatic way. And that's what one of the speakers was talking about. Ben, you were talking about that, right? Yeah. The non-artificial intelligence. Okay, we have maybe time for one more example of that?
Yeah, we'll
Yeah.
go into a break.
Sure. Okay, do you want to do one more example, or
Do one more quick example, and then
Okay.
people can come and stick around for some other ones during the break.
So we had the seeding sensitivity and the texture-based flow viz. We had 7 and 7. So let's do another show of hands if we wanted. So who votes for the seeding sensitivity? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And who votes for the texture-based flow viz? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13. Okay, we'll go with Matt. You're the deciding vote.
What was 14 to 13, wasn't it?
Yeah, it was. So seeding sensitivity.
That's democratic behavior.
Yeah. So this is a problem that is intricately connected with uncertainty, right? Where in space do small changes in seeding position result in large changes to the output or the seeding curvature, right? We can actually visualize that. We can turn that into a visualization problem, right? And see where those unstable or highly uncertain positions in space are. And that's a problem we study, right? And there again is so the overview is we start with our simulation data. That's our starting point. That's your finishing point. That's our starting point. Right? We seed a set of streamlines or path lines, so this applies to both steady and unsteady flow. We compute something called a similarity field, and then we visualize that field. Right? So the key is really computing the similarity field. So the similarity field indicates how sensitive the seeding position is with respect to position. So that's the. So what we're going to see is in this particular visualization, the highly sensitive regions are highlighted in red, right? We're using something called volume rendering to depict the sensitivity field in this case. So the most sensitive regions, or the regions that result in the highest uncertainty with respect to your seeding curve, are highlighted in red, and the less sensitive are highlighted in purple. Right? So the more turbulent regions are in red, and the more laminar flow is in purple or dark blue. Right? And how many people here have heard of volume rendering before? Anybody heard of volume rendering? Okay, not that many people. So it's using semi-transparency. One of the strengths of volume rendering is we're not using explicit surfaces. Like surfaces imply certainty, right? When you see a surface, it says, I am 100% certain about this surface. That's the implicit message. But that's actually a false message, right? You'd rather see surfaces that are not certain, right, that actually convey some fuzziness. And that's what volume rendering, that's one of the strengths of volume rendering, right? We're seeing areas or volumes rather than infinitely thin surfaces. This is a slice through some unsteady flow data, and again, the sensitivity is mapped to color, right? This is a highly sensitive streamline seeding region, so if you position your streamlines here, suddenly the variation in the curvature is going to jump, and that's what we're doing here. We're taking our seeding curve, and we're explicitly showing, okay, here's what happens to the streamlines when you move them over in this sensitive region. Right? And the same again here. This is the Hurricane Isabel simulation, right? And it's showing the sensitive and the sensitive areas for user interaction versus the not so sensitive areas, right? So you can imagine using this as a basis for a streamlined seeding algorithm, right? You place more seeds in the areas of high uncertainty and fewer streamlines in the areas of low uncertainty. This is an example of the Lorenz attractor. It's a more academic example, probably nobody here has studied that. Right? This is a seeding rake, seeding plane that's showing the sensitivity in space as the user turns the seeding rake or rotates the seeding rake in space along the sensitivity plane. So this is somebody using the sensitivity information to see streamlines along the rake, right? And the histogram is showing the amount of sensitivity along the rake positions, right? So we can start out with a very dense rake, for example, and we can change it, the number of streamlines depending on the sensitivity, right? And this is the rake automatically adapting, so automatically seeding more streamlines in areas of more sensitive flow variation. Okay, how are we doing for time? Sure. So that's all of the videos, by the way, and examples that we saw and didn't see are on YouTube. So if you're interested in seeing those examples, they're all on YouTube. Just YouTube my name. And one last thing to wrap up is the Department of Computer Science at Swansea University and the Department of Engineering, by the way, at Swansea University, are applying for a doctoral training center bid with the EPSRC. Starting in January, well, the bid application process is roughly starting in January. Well, we've already started working on it, but the official announcement will come in January 2018. If you're in industry and you're interested in having a PhD student in data visualization, for example, come to your company and work at your company for a little while, maybe permanently after they get their PhD,